I'd just like to introduce Laurel and tell you a little bit about her background. Laurel is a research scientist from Silent Spring Institute, and she has expertise and experience in environmental chemistry, environmental engineering, and risk exposure assessment, She leads the Institute at Cape Cod Water Quality Research and does research on fluorinated chemicals and other compounds of emerging concern. And before joining Silent Spring, she was a research associate at Harvard School of Public Health, and Dr. Schrader received her master's degree and PhD in environmental engineering at the University of California, Berkeley, and a bachelor's degree in environmental engineering science from MIT. She has taught ecology and environmental engineering courses at MIT and Northeastern University. I welcome Laurel here today, and the two of us are going to try to talk about groundwater issues and emerging contaminants. We've done presentations together in the past, and I think these merge together nicely. Laurel will give us more of a regional perspective and global perspective, if you will, and then I will focus on Eastham's most recent experience with the Eastham landfill. And again, welcome, Laurel, and thank you so much for joining us today.
All right, is this on? Great. Well, it's nice to be here today. Thanks, Jane, for having me. We've been talking about doing something like this for a couple of years now,
yes.
So I'm glad that we finally were able to make it happen. As Jane mentioned, I'm a research scientist at Silent Spring Institute. We're a nonprofit research organization dedicated to understanding links between everyday chemical exposures and health. We have a particular focus on women's health and breast cancer, and we were founded over 20 years ago due to concerns about elevated breast cancer incidence on Cape Cod. We've had an active water quality research program for about 20 years, focusing on endocrine disrupting compounds and other contaminants of emerging concern. So for today, I want to start by talking about some of the challenges facing Cape Cod water quality, give an overview of contaminants of emerging concern for those of you who may be less familiar with the topic, give you just some key highlights of our water quality research. I could spend a couple of hours going into the information at great length, but I'll just provide some highlights, and then step back and think about some lessons learned and steps moving forward. So I hope that you saw this article in the Boston Globe magazine last summer. Here on the Cape, we think a lot about nitrogen and coastal water quality, and I thought that this article did a nice job in also reminding people that drinking water on the Cape, on parts of the Cape, is threatened and that it's an important resource that needs to be protected. And that's a message that we've thought about for a long time as well. This article is also great because it is a nice picture of Jane that she loves. And following in this vein of a precautionary approach to water quality, Cheryl Osimo, who's our Cape Outreach Coordinator, and I wrote an editorial in the Cape Cod Times last fall as well, kind of advocating for a precautionary approach to drinking water quality. We often kind of handle drinking water as a red line where we are either above some guideline or standard and it's a imminent problem, or we're below it and everything's okay. And we're thinking about, even if we're not above a guideline, who wants landfill leachate or firefighting foams or wastewater to be in their drinking water? How can we be more precautionary in our approach? So in that vein, this is the precautionary principle. The definition is basically better safe than sorry. Like, we don't necessarily need to have definitive scientific proof before taking action to avoid risk. So we think a lot about nitrogen here on the Cape, and in terms of drinking water quality, there are certain contaminants that are regulated, like nitrate and lead, and those are sort of well understood contaminants. But today I'm talking about sort of the new frontier in contaminants, what I like to call the next generation in drinking water contaminants. So what am I talking about here? So we use this term, contaminants of emerging concern, or emerging contaminants, and I just wanted to break down like what that term means. So contaminants, these are considered contaminants because chemicals like pharmaceuticals, we don't expect them to be in drinking water or in groundwater or in lakes. So the chemicals that we think about a lot are widely found in the environment. In some cases, these chemicals are considered emerging because we know that every year new chemicals go into production in production for consumer products, for instance. But in many cases, these are considered emerging because we have improved analytical techniques that allow us to measure lower and lower concentrations. So we're looking now at parts per trillion or nanograms per liter levels. And the analogy I like to use is to think about looking at the night sky with, say, a handheld telescope, and you see some stars. And then if you went to a really good observatory and they had a very powerful telescope, you'd see many more stars. Of course, the sky's the same either way, but your ability to see what's there is improved with better analytical capability. And then why are these of concern? So many of these chemicals are either of concern because they pose potential human or ecological health risk. Of course, it's a lot easier to think about risks to fish or other aquatic organisms because you can put them in a tank in your lab and study them throughout their whole life cycle. And there are a lot of concerns about hormone disruption in particular that can affect the reproduction and behavior of fish. For instance, in rivers downstream of wastewater treatment plant, researchers have found a high proportion of male fish that are feminized and maybe have female proteins or actually contain eggs. And so that sort of raised a lot of concern about these emerging contaminants from an ecological perspective. From a human health perspective, of course, the questions are a lot harder to answer. Many of the chemicals that we're finding in drinking water at high levels of exposure have been linked to certain human health effects. But we're still learning more, and there hasn't really been much investigation of chronic exposure to low levels of many different contaminants in our drinking water. So there's no set list. You could say, well, what exactly is an emerging contaminant? And there's no set list, but there are some types of chemicals that people typically think about. So one common source of contaminants of emerging concern in the environment is household wastewater. So if you think about all the products that you have in your home, they have many different ingredients. So I'm an environmental chemist. I look at these products and I think, okay, we've got flame retardants and pharmaceuticals and hormones and antimicrobials and flame retardants, and all of these are ending up in the environment. Household wastewater is not the only source of contaminants of emerging concern, but it's often what people think about. So how do these contaminants of emerging concern get into the environment? So here's kind of a general picture that people use to think about all the different sources. So we've got residential wastewater, maybe going to a wastewater treatment plant. There's medications at hospitals. There's runoff from agricultural activities, maybe antibiotics that are used for livestock. Of course, on the Cape here, most people have a septic system. So this part is really an important component when thinking about sources of contaminants of emerging concern. There's not a ton of agriculture. We don't really have a lot of industries here. And our wastewater mostly goes through septic systems. So how well do septic systems and wastewater treatment plants remove emerging contaminants? The question is, it depends. Neither wastewater treatment plants nor septic systems are designed to specifically remove emerging contaminants. They're designed to remove solids, to reduce biochemical oxygen demand, and in some cases to address nutrients. Some emerging contaminants will be removed anyways. And the extent of that removal depends on the type of treatment. So if you have an advanced wastewater treatment plant or an advanced on-site system, you have a better chance of removing emerging contaminants. And the extent of removal also depends on which individual chemical you're looking at. So some chemicals just naturally, based on their chemical structure, tend to break down, and microbes can easily break those down. So they have a high biodegradability. Some compounds are more hydrophobic. That literally means water-fearing. So these are chemicals that tend to stick to soils, so they maybe are better removed in a leach field, or they tend to stick to sludge in a wastewater treatment plant. So they may not be discharged to surface waters, although they might be persistent in the sludge. And then for a subset of emerging contaminants that are volatile, say fragrance compounds, there's also the potential for them to end up in the air. So I want to talk for a couple minutes about a specific class of emerging contaminants that I've spent a lot of time thinking about. The name is kind of a mouthful, per- and polyfluoroalkyl substances, PFASs. We used to call them PFCs, but now we're supposed to call them PFASs, or maybe more simply, highly fluorinated chemicals. So these are a class of highly persistent man-made chemicals. And probably all of you have traces of these chemicals in your body. If you think of your home and anything that contains Gore-Tex, Scotchgard, Stainmaster, Teflon, even certain types of dental floss contain fluorinated chemicals. They're very useful because they make products grease-proof, waterproof, stain-resistant. But there are also concerns about these very persistent chemicals. A few chemicals have been studied extensively. These are called long-chain PFASs, and they tend to stay for a really long time in our body. And those specific chemicals have been linked to cancer, developmental toxicity, immune system suppression, and other health effects. These long-chain compounds that we know the most about, for the most part, their production in the US has been phased out, although they're still produced in China and other parts of the world. And in their place, we now have other fluorinated chemicals. Many of these are shorter chain versions of the ones that have been phased out, but there are a range of different chemical structures that are used. And the manufacturers say, okay, we know that the long chain ones are harmful, we don't make them anymore, the short chain ones are fine. But I would say that they still raise health concerns because they're still persistent. These carbon-fluorine bonds that are their trademark are very persistent. So these chemicals don't break down. They're chemically similar to the ones that we've phased out. And some preliminary studies have suggested that they might have similar biological activity. And just from a precautionary point of view, it seems like if we know that the long-chain compounds are harmful, there's a good probability that at least some of the shorter chain ones are as well. And so some scientists are advocating for more of a restriction on the whole class of compounds rather than phasing out one chemical and replacing it with a similar one. The same thing has happened with BPA. You've probably seen BPA-free plastics, and you think that's great. It doesn't have that harmful chemical anymore that I'm worried about. But what's in it instead? BPS, which is almost the same thing and also a hormone disruptor. So when we just try to deal with chemicals one at a time, we often have this phenomenon of regrettable substitution, where we put in one chemical that we don't know if it's harmful to replace one that we do. In terms of environmental contamination related to these highly fluorinated chemicals, another really important source are certain firefighting foams called AFFF that are used to put out fuel fires. So they often end up as groundwater contaminants near airports and near fire training areas. So most of my talk today is about water, but I did want to mention that we're also thinking about other pathways of exposure. And as you can imagine, we're all exposed to these chemicals in many different ways. So another place where you find fluorinated chemicals are in certain types of food packaging. So for instance, microwave popcorn bags, pizza boxes, and fast food packaging. So I was actually the lead author on the study that came out on a couple of weeks ago looking at highly fluorinated chemicals in fast food packaging. So for instance, grease-proof wrappers for sandwiches or burgers or little pastry pouches, some of those contain some of these same fluorinated chemicals to make the paper grease resistant. So this paper, I think it's safe to say, went viral because it was covered in a lot of serious media outlets like CNN and Washington Post. But the one I'm most proud of is The Onion, which is a satirical online newspaper. So you know you've done something important if you've made it into The Onion. And regardless of where you fall on the political spectrum, The Onion can make you laugh. So that's just a little side note and a reminder that drinking water is not the only concern in terms of exposure. In terms of drinking water contamination, fluorinated chemicals are a concern nationwide. This was a study that I was also a co-author on that came out last summer, looking at public water supplies across the US and showing that water supplies that were in the same watershed area as production plants, so near a 3M or DuPont facility, near military fire training areas, near airports where they're certified to use these AFFF firefighting foams, and ones near more wastewater treatment plants were more likely to have these highly fluorinated chemicals. So as I said, Silent Spring Institute has been studying water quality on the Cape for many years, and today I just want to give you some highlights of our key findings. We've been measuring CECs in Cape Cod public and private drinking water wells, in groundwater, in ponds, and in septic systems, trying to understand which chemicals are most present in the wastewater and what happens to them as they move through the environment. The types of analyses that we do to measure traces of pharmaceuticals or fluorinated chemicals are very expensive, and so they're not part of routine water quality testing. But we are interested in identifying which wells are most vulnerable to having these types of chemicals. So we've also thought about what types of markers can best predict CECs in public and private wells in the Cape. What if we look at land use? What if we look at things like nitrate? Do they tell us something about these contaminants of emerging concern? We're also very interested in informing Cape wastewater management and drinking water protection. That's why I'm here today. Again, on the Cape right now, everyone's thinking about nitrogen and coastal water quality, and it's great to see that important issue getting a lot of attention. We just want to make sure that at the same time that towns are thinking about where are we going to put our wastewater, how should we treat our wastewater, that we're also thinking about the other chemicals that are in that groundwater and making sure we're, in the long term, thinking about our drinking water quality. So we conducted 2 companion studies on public and private wells across Cape Cod. And some of the most frequently detected chemicals that we found in our studies were an artificial sweetener called acesulfame. So many products and low-calorie yogurts and juices contain this artificial sweetener. It passes through our body without breaking down. That's why we don't get any calories from it. It also seems to pass through the environment without breaking down. So that was one of the most frequently detected chemicals. We found certain pharmaceuticals like antibiotics and anticonvulsants, for instance, carbamazepine, which is also used for bipolar disorder. We found some flame retardants that are commonly used in home furnishings. And we found some of these highly fluorinated chemicals. So for instance, PFOS is one of the long-chain compounds that's being phased out in the US. And we also found its shorter chain cousin, PFBS, which is one of the replacement compounds. In terms of the levels that we found, typically when we did detect these chemicals, the concentrations were on the order of 1 to 10 parts per trillion or nanograms per liter. And I'll talk in a few minutes about how we might put that level into a context. I would note that when we picked which wells to test, we included wells to include a range of situations and a range of likely wastewater impact. So we included some that we thought would have no or very little human impact, low nitrate wells in fairly pristine areas, and then some that we thought would be among the most impacted. When we compared our results to what's been found in other parts of the country, we found that the highest level that we found on Cape Cod was basically as high as had been found in other source waters across the US. So I did want to note that, as part of our study, our public and private well studies, we did include these highly fluorinated chemicals. So in 2010, we published a report here on the Cape with the results of our public well study. And we found PFASs, specifically the 2 long-chain compounds, PFOS and PFOA, in a number of the wells that we tested. A couple of the wells were relatively high. These were wells in Hyannis that seemed to be impacted by some of these firefighting foams. And subsequent testing as part of what's called the UCMR program. It's an EPA program to test for unregulated contaminants so that they can get a better picture across the country of which unregulated contaminants they should pay attention to, which are most common. So follow-up testing in 2013 through 2015 showed that, yes, these Hyannis wells had relatively high levels of these fluorinated chemicals coming from the county fire training area, likely from the airport. There's also other industries in that area. And we've also thought about the potential role of septic systems and wastewater as a source to certain wells as well. The drinking water for many years has picked up these fluorinated chemicals from the firefighting foam. That means that the septic system wastewater, which is basically made up of drinking water, also has those same contaminants. So there was a little bit of a cycle, perhaps, where some of those contaminants went into, from the drinking water into the wastewater and back into drinking water. We also found low levels of many fluorinated chemicals in the public and private wells that we tested. And in some cases, we think that this could be coming from septic systems. We did see some relationship where wells with higher nitrate or wells in more densely developed areas seem to have more of these fluorinated chemicals. And given that they're present in so many household products, it's not surprising that our wastewater picks up traces of these chemicals as well. We had a couple of other wells that seemed to have relatively high fluorinated chemicals that didn't seem to come from wastewater, and those could come from maybe commercial wastewater or potentially from landfills. And you'll talk more about the Eastham landfill, and something that I think about is that landfill leachate is also contains elevated levels of fluorinated chemicals. People throw out their stain-resistant couches or rugs or apparel, and those chemicals, because they're so persistent, can end up in the leachate. We've learned some general lessons as well about the types of wells that are most impacted by emerging contaminants. As you might expect, wells that have more development around them, more septic system discharges in their recharge areas, tend to have more of these emerging contaminants. So this is from our study of public wells. We categorize the extent of unsewered residential development around each well, and we see higher pharmaceutical concentrations in wells in more densely developed areas. And we saw similar trends in our private well study and also in a study of ponds, where we saw higher levels of pharmaceuticals and hormones in ponds that had more upgradient development. We've also thought about chemical markers for contaminants of emerging concern. And one that comes to mind is nitrate, because all public water supplies have to test for nitrate. A lot of private well owners test for nitrate as well. And on the Cape, we know the largest source of nitrate into groundwater is septic systems. So it makes sense that wells with higher levels of nitrate would have more emerging contaminants. So we do see that trend. Again, this is from our public well study, but we saw similar trends in our private well study, where wells with higher levels of nitrate tended to have more of these emerging contaminants. We also evaluated several other potential markers of emerging contaminants in public and private wells. So one example is boron. So boron is used in certain soaps and detergents. It's been used in other studies as a marker of wastewater. And we found a correlation where wells with higher boron also had more emerging contaminants. And it's helpful to have the nitrogen and the boron together, because you could imagine some wells have high levels of nitrogen from fertilizers or from other sources. So where you see both the nitrogen and the boron high, that gives you more evidence that that might be coming from wastewater. In terms of all the emerging contaminants that we tested for, the one that seemed like the best marker was that artificial sweetener acesulfame. Wherever we saw any pharmaceuticals or flame retardants or fluorinated chemicals showing up in our private well study, we always saw this artificial sweetener. And then we also saw an association with well depth. Shallower wells tended to have higher levels and more frequent detections of emerging contaminants. So what does this all mean? So we found parts per trillion levels of things like pharmaceuticals in drinking water. How concerned should we really be? Well, as you can imagine, this topic has been a great material for political cartoons. We've thought a lot about how to put these results into a context. So I think that it's important to keep in mind that when we take a medication for a specific medical condition, we ingest, say, milligrams per day of that active pharmaceutical ingredient. Through your drinking water, you might get nanograms per day. So that's like 1,000,000 times less. And you can do the calculation and figure out how many glasses of water you'd have to drink to get a therapeutic dose. And some people kind of stop there, and then they say, well, this just can't be a problem because you'll never drink that much water. And then it's also important to note that if you have a stain-resistant carpet or flame retardants in your couch at home, that your exposure directly to having those products in your home likely results in higher exposure than through drinking water. And sometimes the drinking water superintendents say, why are you always picking on drinking water? We could have our water be perfectly clean and people will still be exposed to these. And I think that that's a fair point, and it's important not to necessarily blame water suppliers, because they're sort of at the receiving end of all the products that we use. But I would also say that there's something really basic about water. And once we put these chemicals out into the environment, they stay there for a really long time. Whereas we can decide we're going to buy a new carpet or we're going to take out certain products from our home and we can make that change quickly. It's hard to change what we've put into the environment and what will be in our water for a long time. And then in terms of orders of magnitude, for chemicals that are regulated in drinking water, say solvents or pesticides, we're often thinking about parts per billion or micrograms per liter concentrations as being of concern. And now we're at nanograms per liter or parts per trillion. So we're kind of a few orders of magnitude lower than where we're used to thinking about other types of contaminants. So as I said, some people say, okay, you need 18 million glasses of water. This clearly is not a concern. But I think that the presence of these chemicals in drinking water does raise concerns for several reasons. In the case of pharmaceuticals, we know that these are designed to be biologically active and potent, and we don't intend for everybody to be exposed to them. We know that children and infants are particularly sensitive to the effects of many chemicals, such as pharmaceuticals. And we know that certain people are especially sensitive. So some people are sensitive to antibiotics. So even though these concentrations are well below a therapeutic dose, they still raise concern because we don't expect everyone to be exposed to them all the time. There's also the potential for synergistic effects of chemical mixtures. So some lab studies have suggested that there can be biological effects from certain mixtures of chemicals that they don't observe when they study each chemical individually. And a new type of concern that scientists are thinking more and more about are endocrine disruptors or hormone-disrupting chemicals. So typically when risk assessors decide whether a chemical is harmful, they look at studies of high levels of exposure, we see some health effect, and then we make an assumption that we'll see less of an effect at a lower level of exposure. And for some endocrine disruptors, scientists actually see effects at low levels of exposure that they don't see when they study high levels of exposure. So there are concerns that we might be missing some low-dose effects for endocrine disruptors. So thinking about drinking water regulations. So the emerging contaminants are not regulated in drinking water. Some, such as PFOS and PFOA, have health guidelines. So they're kind of like standards, but they aren't enforced in the same way. And we tend to think of them as a bright red line. So if we're over it, it's a problem. If we're under it, everything's okay. Of course, it's not that simple. We know that it's not like such a bright red line, that it's more of a gradient. And it's also challenging because over time, we learn more and more about potential health effects, so those standards or guidelines can change over time. So just as an example of that, this slide is meant to be kind of messy and confusing. Basically what it's showing are health guidelines developed by EPA and by individual states for two fluorinated chemicals, PFOS and PFOA. These are those long chain compounds that are being phased out. And some of the newer guidelines look at the combination of the two. Some of them look at each one separately. And what you see is that they're very variable. Over time, they seem to be going down as we learn more and more about potential health effects. But even if we were going to treat these as a bright red line, the question is, where would we put that line? So it makes sense to approach these maybe from a more precautionary point of view and to think that over time some of these might go down. So let's not aim to just be a little bit below the guideline, but when we can, to try to stay well below what we currently understand to be a helpful guideline. So I'd note that in 2016, the EPA lowered its guideline for PFOS and PFOA. So in 2009, they established a guideline of 400 and 200 parts per trillion. And then on a Friday afternoon, they changed it to 70. So systems like Hyannis that had wells that were below the old guideline but above the new one, overnight, suddenly were no longer meeting this new guideline. Again, this isn't a standard. They didn't have to do anything about it, but to their credit, they did take steps to put in new treatment and to purchase water from other towns that did not have the same contamination. But it led to this sort of crisis because suddenly they were above a guideline, and it would be nice to think that we could take a more forward-looking approach, I guess, and not have this be a crisis where it's like we're below a guideline, it's fine. Oh, now we're over the guideline. Now we have to do something right away. And so they actually had a do not drink advisory in effect for a month and a half for pregnant women, breastfeeding mothers, and children while they worked to bring the water system under that new guideline. So what are some lessons learned when we step back and think about our findings over the years? So one lesson that I take away is that high levels of known contaminants may indicate the presence of unknown contaminants. So some examples include high levels of nitrate indicating the presence of pharmaceuticals and flame retardants and other contaminants that come from household wastewater. If you look at the wells in Hyannis that had the highest levels of fluorinated chemicals, it wasn't exactly surprising that they might be the ones that had the highest levels of fluorinated chemicals. Some of these wells in the past have been treated for volatile organic compounds coming from the airport or for perchlorate coming from the fire training area. So we've seen chemicals in those wells in the past. The presence of those known contaminants could be seen as a marker for other contaminants that people didn't even know to measure 5 or 10 or 20 years ago. We can also think about proximity of wells to pollution sources. So for instance, wells that are close to a landfill, it's not surprising that those wells were most likely to have 1,4-dioxane or other contaminants that might come from landfill leachate. Again, the wells closest to the fire training academy were the ones that had the highest levels of fluorinated chemicals. Another lesson I'd say is to heed early warnings. So I would put out there that in 2010, we let people on the Cape know about fluorinated chemicals, and we were the first to point out that the wells in Hyannis were vulnerable to these contaminants. We didn't test the ones near the fire training area, so we didn't see those highest levels. But we put it out there. The County Fire Training Academy did change its policy as a result of our work to no longer, well, their policy changed. I think in reality, fluorinated foams were still used. But they changed their policy to no longer allow the use of fluorinated firefighting foams there. But in terms of steps for treating the water or identifying new drinking water sources, that didn't really happen until there was a detection over a drinking water guideline, and then that really prompted action. Another example that I thought was kind of interesting, so again, the EPA required all large public water suppliers in the US that serve over 10,000 people to test for 6 highly fluorinated chemicals between 2013 and 2015. Again, this is part of their unregulated contaminant monitoring rule. It gives them a sort of a snapshot of the types of contaminants that are common in US drinking water and helps them prioritize which ones they should regulate in the future. So these were all the water supplies in Massachusetts that had detectable levels of fluorinated chemicals. I would note that the detection limit or the sensitivity of the tests that they used was not very high. So the ones where these chemicals showed up, I'd say, are probably the tip of the iceberg. I bet that there are other water suppliers that did have these same chemicals, but just at lower levels. So you can see that Hyannis had by far the most number of detections and the most chemicals detected. And then there was this one in Mashpee. Out of all, they tested a whole bunch of times. They only had one detection of one of these chemicals just over a guideline. There's no guideline for this particular compound, PFHXS. I don't know if anyone sort of paid attention to this guideline, but it was just one, and I could see how you just not really pay attention to it because, it just happened once. But then I noted that in fall of last year, that at a community area close to that well, they found PFOS and PFOA together at concentrations above that new health guideline. And that was probably from something coming from Joint Base, Cape Cod. That's another source of these fluorinated chemicals because they use those same firefighting foams. So you might take away the lesson that if you looked at this and said, okay, this isn't necessarily that high a level, but where's that one coming from, and are there higher levels in other water supplies that are close by? So it's kind of a heed the early warning, again, even if you're not over a guideline. And then I guess remember the precautionary principle and thinking about the editorial that we wrote. Even if you're not over a guideline, do you really want to be drinking water that contains landfill leachate or firefighting foams or wastewater if we can take steps to avoid it? And it seems prudent, especially as we're doing long-term planning for wastewater management and drinking water protection, to take these kinds of things into account so that we don't have this crisis when we do happen to have a guideline that's lowered or we do find something that's over a guideline and we have to react to it kind of in a really reactionary way. So I've also been thinking about how can we incorporate our work and our concerns about emerging contaminants into the nutrient management questions. Just dealing with nitrogen and adding in phosphorus has been a huge challenge for the Cape. And here we are, we're talking about potentially thousands of additional chemicals that we should consider. We don't know a safe level. We don't know exactly which ones are of greatest concern. I'm trying to think about ways to helpfully include this kind of information without just creating a lot more uncertainty. And so I've been thinking about kind of the toolbox of approaches that Cape communities are developing, constructed wetlands, aquaculture, eco-toilets, all the different ways that are being evaluated in terms of their ability to remove nutrients, and can we sort of overlay with that toolbox available information about how well these approaches could deal with emerging contaminants and where they would deal with them. So for instance, if we think about shellfish aquaculture, that can do a great job of reducing the levels of nutrients within a water body. And so they have the potential to absorb some of those contaminants as well. So we might want to think about what's accumulating in the shellfish, but it's also important to keep in mind that we're only just dealing with the water body itself. So we're not removing those contaminants from the groundwater in that watershed. And maybe if there are no drinking water wells in that area, maybe that's not a concern. But if there are public or private wells that are in that area, maybe we would look to approaches that might divert or treat the emerging contaminants at the source. So we partnered with the town of Falmouth. They were doing a pilot study to look at eco-toilets. So composting or urine diverting toilets in your home as a way to divert nutrients from wastewater right at the source. And we thought about, what are the types of contaminants that might be diverted, like pharmaceuticals or hormones that our bodies excrete, and which types would not necessarily be diverted, say chemicals associated with detergents or fluorinated chemicals that probably get into your wastewater other ways. So as we move forward, we're thinking about ways where we can sort of inform this toolbox and where can we fill in some gaps in terms of knowledge about emerging contaminant removal. So some steps for what can residents do, and maybe thinking a little bit more broadly than just drinking water, but thinking about good stewards of our environment and how can we best protect the health of our families and our homes. So supporting local efforts to protect open areas is one way to protect water quality. As we've seen, if you have water supplies or ponds that are in more pristine areas, they're better protected from these emerging contaminants. We can all reduce our reliance on harmful household chemicals. That's kind of good for our immediate health as well as good for our impact on the environment. Not flushing hazardous chemicals or dumping products on the ground. If you have a septic system, to be sure that you're maintaining your septic system. Again, not all emerging contaminants will be removed in your septic system, but if your leach field is functioning properly and the soil is well aerated, you have a better chance of removing emerging contaminants. You can learn where your water comes from. If you have a private well, it's sort of up to you to monitor your water quality over time. And if you see contaminants in your water, to consider getting a water filter. Again, you have to know what's in your water to know how to treat it, though. And more broadly, supporting consumer and regulatory action to improve the safety of chemicals in products, and to promote more testing of chemicals before they go into products rather than dealing with them afterwards. And I would just put a plug in for our smartphone app called Detox Me. It's got lots of great tips for how you can reduce exposures to harmful chemicals in your home. It can send you reminders. You can look up recipes for do-it-yourself cleaners. So I recommend that you check that out. So the work that I talked about today has been supported by many people on our staff and others. I can't really fit everyone on the slide, so I'll just say that this work represents contributions from many people and contributions from many funding sources. And if you want to know more about our work, read any of our papers or fact sheets, you can go to silentspring.org/water. So thanks again for coming, and thanks, Jane, for inviting me.
All right. Thank you so much for joining us today on this dreary day. And I want to start off with one very important message. There are 33 days until spring. So something to look forward to. And daylight savings time begins on March 12th. So that's a reason to smile, because it usually seems like I'm talking about gloom and doom. And so I want to start out with something pleasant. Again, thank you so much, Laurel. We gained so much from her presence and her participation in these events, and it really is an ongoing message that we're trying to deliver and to stay focused on, that there's a long long history of issues related to our very sensitive peninsula here, and we need to stay focused on what we can do proactively to protect it. So we are going to focus now on something that's right in our backyard, the Eastham landfill. And we're going to talk about some of the historic information related to the Eastham landfill, which I think are shared by other communities. But in particular, we had our focus on our water supply issue with our residential wells. So in effect, we parallel very closely with all that Laurel just presented, but we're going to give you the local perspective. So with that said, I'm going to start off with my overview, which we're going to talk a little bit about the history of Eastham landfill, the environmental assessment that followed, solutions to the problem, the lessons learned, and maybe a take-home message of what we do from here as citizens. You're all residents here for the most part. You know where we're located. Eastham is about 14 square miles in size, and we have a year-round population of 5,600, thereabouts. However, we're a seasonal community where 50% of our homes are non-resident taxpayers, and our population swells from this low amount of a year-round population to 30,000 people in the summer. And we also have a lot of transient visitors that join us with visiting our seashores and beaches and so forth. So the impact on our environment is really significant. And so as the density and development has continued over the last 20 years, so have our resources been affected. So the Eastham landfill, in some of the basic history about it, it's about 10 acres in size. It was operated, like most communities, as a solid waste disposal site from the late 30s to the early 90s. In 1997, we had it capped. This capping closure was accomplished according to the regulatory requirements supervised by the Department of Environmental Protection. And as in accordance with that closing procedure, we had a monitoring plan which we followed. And because we had residential wells down gradient of our landfill site, a lot of those residential wells were incorporated into our monitoring system. This isn't ordinary. Usually you just have monitoring wells, but we in fact used many residential wells as part of our network and surveillance system. So we were required to test for a vast array of contaminants, and we are subject to a very high regulatory standard called the GW1 standard because we obtain drinking water from the groundwater. So we're held to a very high standard. Our problem developed during one of our routine monitoring occurrences in November of 2012, where we detected an exceedance of an emerging contaminant of concern, 1,4-dioxane. The result of this discovery led us into what's called an IRA plan, an immediate response action plan. And as such, we're responsible to conduct this according to all the requirements of the Department of Environmental Protection. The exceedance occurred at a monitoring well right on the face of the landfill. Our first response after this occurred was to test the adjacent wells because, as Laurel said, the most likely source of this contaminant was going to be from the landfill, and we anticipated there was potentially going to be impact to residential wells, which in fact there was. And as we detected the exceedance, which we feel migrated from the landfill, we expanded the monitoring plan and immediately provided bottled water to all households that were affected. Our responsibilities to this day are continued reporting to the Department of Environmental Protection until this site is adequately regulated and the extent of the 1,4-dioxane is determined. We are near a completion of the study at this time. Once we do obtain those objectives, this monitoring program will revert back to the solid waste program under the supervision of the Department of Environmental Protection. So for all of us to just sort of situate ourselves, I have some slides that just show the site location in general. And the yellow box is the Eastham landfill, and you can see we have water to the east and water to the west. The Route 6 line actually is important because it's almost the height of the groundwater lens, so it's a really important boundary. And you can see this study advanced, the line depicted in the yellow was really the extent of the study area, as we called it, where we tried to obtain samples from residential wells. The blue lines in this case, let me see if I can point here and here, show the general groundwater direction that emanates from the landfill in a southeasterly direction. So a little bit about the geology and the contaminant profile. The depth to groundwater around the site of the landfill is about 45 feet to groundwater. And the soil strata is pretty much sands and gravel for the first 60 feet, and then we have discontiguous layers of silt and clay. And at the very low depths of 150 feet from ground surface, we have stratas of blue clay. So just as Laurel had said, in the shallower aquifer, what we're seeing really are higher levels of nitrate, higher levels of iron, and at groundwater at very deep depths, we're seeing volatile organic compounds. We have had past experience with doing extensive hydrogeology in this area from earlier studies with vinyl chloride. In that particular case, we saw at the very deep depths of the groundwater, particularly at a distance out from the landfill, that we were pretty confident that those were, in fact, plumes from the landfill. So what was the problem? The problem was 1,4-dioxane had impacted private wells. So we really had to come up to speed with what the problem was. We had to wrap our hands around how we had to deal with this problem. Historically, 1,4-dioxane is a solvent stabilizer, and it's actually a byproduct of an industrial process. It's highly miscible in water, very mobile. It has high leaching capacity, and it migrates through the soil. And its physical and chemical characteristics are resistant to degradation. And lastly, the methods to remove it from the environment are generally ineffective and very expensive. This was a huge problem. What makes it even more of a problem for our municipality was the lack of municipal water. So because we had no municipal water as a backup plan to provide these residents down gradient, we had a real issue to deal with. So we had, as a community, supported the development of a municipal water system since the early 70s. Unfortunately, those plans did not pass at town meeting, and 1,4-dioxane was not actually the focus of the earlier support for municipal water systems. It was actually related to other factors such as high nitrates, high minerals, and the fact that we had no fire protection. So we had, unfortunately, reached a crisis with this occurrence. This is not a good place to be in. So what is 1,4-dioxane? Since this was the chemical we had to deal with, we learned a lot about it. It doesn't occur naturally in the environment. And again, it's an unintentional byproduct of an industrial process that makes surfactants more usable, if you will. It mixes easily with water, and it's been found to contaminate groundwater throughout the United States. The U.S. EPA classifies this as a likely carcinogen due to its ability to cause cancer in laboratory rats and mice. So again, this is not a chemistry class and not a chemistry exercise here, but the point here is that It's a chemical process used in industry to make surfactants less abrasive. So it's an unintentional byproduct. So where did it come from? Paralleling what Laurel just told us about in her presentation. It comes from land use sources. So if we have an area such as the landfill, let me try to go back. And it gets into the fresh groundwater table. We happen to have a well down gradient. The well is going to uptake that contaminated water before it's discharged to the ocean. But we also know that it's discharged in wastewater. So in the course of our investigation, this was a really confounding experience for us, because we were left not really knowing, was the source entirely the landfill, or was the source partially the landfill and partially wastewater? So likewise, if you have wastewater discharge of household products that contain 1,4-dioxane or other emerging contaminants of concern that Laurel just told us about, and again, your well happens to be down gradient a source, such as your neighbor's drain field or your own, and that well uptakes that water for drinking purposes, you are potentially consuming contaminated water. So let's talk about some of the sources of 1,4-dioxane. Again, two-sided conversation. There are industrial products and there are personal care products. So we know some of these include solvents, degreasers, paint strippers, varnish, etc. On the personal care product side, these include products we use every day, products we dispose of every day, Tide, bubble bath, children's shampoo, and my favorite, Mrs. Meyer's dish soap, which I thought was so green. And the consumer issue that makes it even more complex is the FDA regulation and process by which this product, 1,4-dioxane, and I'm sure many others, are not listed on the ingredient label because it's a co-contaminant. And we don't know if the manufacturer has in fact removed that co-contaminant. So it really creates a dilemma for us. So I'm going to move on now from the problem to what our investigation informed us of. So this was an extensive environmental investigation that included more than 400 residential homes at great expense to the town. What we found in our extensive environmental assessment, that I could almost break this down into a 50-50 conversation, because you'll see that 12.5% of the wells tested exceeded the guideline. 48.5% there was some level of detection, and 51% had no detection. So if you want to basically consider this a moving scale, as Laurel was saying, things move, things change, 50% of the wells tested had some exposure, 50% did not. So when we look at the numbers, this is a huge investment for our community. It's very expensive to test for these chemicals. You also have to send out trained personnel. There's chain of custody involved. It's very expensive, and it gets never-ending. It's a never-ending hole that you fall into. But in our case, about 39 homes exceeded a drinking water guideline, not a standard, but a guideline that we did follow, and we needed to supply those in homes with a temporary solution to the problem, which was a delivery of bottled water. So 39 homes were on bottled water within this red area, which was depicted as the mandatory hookup area. We'll get into that a little bit later. So of those 410 homes tested, that's the number of households that were receiving bottled water. So let's get to the solution. Bottled water was not a permanent solution. We really needed a permanent solution for all times, and that really was a safe supply of drinking water from a remote location. Fortunately, the effort to obtain that objective started long ago. You can see the voter history here. We began the effort for municipal water that involved the support of many of you starting many years ago. So in 2007, we started to bring this to the voters for consideration. One real key factor here in us being able to react so quickly to our crisis was May 2009, where we did gain approval for the construction and permitting of 3 municipal well sites. You can see this occurred in 2009, and we were very fortunate because this process takes many, many years. It's a very long and difficult process, and each well cost about $1 million from beginning to end, so $3 million went into that work effort. And fortunately, when our occurrence of the detection of 1,4-dioxane happened in 2012, at least those wells were almost completely through that permitting and approval process, which then led us to being able to go back to the town meeting for approval again for a municipal water system, which was finally approved in May of 2014. In May of 2014, it was a partial system. 1 year later, this project was brought back to the community for town meeting approval for town-wide system, which was then approved in May of 2015. So who's paying for it? You are, the taxpayers. This is being supplemented by low-interest SRF loans and grants wherever we can get them. And so the total cost of the project is actually on the tax base. So how is this a solution to the problem? We were asked that in the very beginning when we were developing a municipal water system. How will we be safeguarded? So you can see in the black circled area, that is the groundwater protection district, where we have an overlay of more restrictive regulations. And they are not down gradient of the landfill. Environmental partners, when they were developing the municipal water sites and doing all the work required for the permits, hired McLean Environmental, who looked at flow paths. And you can see they took some of the wells that were contaminated and determined groundwater flow. Another snapshot of that work. And in this slide, they determined the approximate length of time for travel. So if we step back further, we are looking now at the watershed that encompasses a portion of this landfill study area. And it seems pretty clear that the landfill had contributed to impact to those wells, and now we're faced with almost a complete watershed that has been impacted. This will play into wastewater planning that we are underway considering at this time. This is the focus of the entire area, which we are calling the mandatory connection area, in our agreements under our regulatory responsibility that was determined with our consultant in cooperation with administration and the Department of Environmental Protection. We needed to, in our immediate response action plan, provide the long-term solution. And so this solution included casting a very large conservative net to provide safe drinking water and remove that risk to these homeowners. So in this area, depicted in red, the well connections, plumbing, expense, et cetera, is being paid for by the town of Eastham to eliminate the public health exposure. Within this area, the Board of Health was required to consider eliminating recirculation, again, a theme that was discussed in Laurel's presentation, in the environment. So the Department of Environmental Protection is concerned, one, with public health protection, but they're also concerned with eliminating recirculation of contaminants in the environment and downgradient receptors. So we really, under our immediate response action plan, were required to eliminate downgradient receptors. So we had to negotiate with them and create regulations that would ensure that we would do just that. In trying to advocate for some of the concerns that homeowners discussed with us was potential reuse of their wells that were once for potable purposes for non-potable uses. So we had to be sensitive to their questions and concerns, yet we have a regulatory obligation to eliminate the recirculation aspect. So what the Board of Health decided to adopt as a regulatory mechanism included an area, in this entire area, if you want to keep your well for irrigation purposes, you basically have to apply for a variance. This was a regulatory responsibility we have to meet with the department. We could, through our three-dimensional hydrogeology profiles that were developed through all of this work effort, we could almost draw a line through the middle of the area where there was a higher level of concern from wells at certain elevations and a lower level of concern. So if we did, in fact, drew a line right here. This area in the pink area here is the more dominant path of the plume from the landfill. We had some cross-gradient anomalies that occurred here, which still are really not really completely understood why that happened. The geology in this area, as I said, is very complex. We have two layers that are separate, and in terms of what we're seeing with the aquifers, the shallow aquifer, then some discontiguous layers of clay, then a lower aquifer. In some cases, we think there's cross-gradient movement from the lower aquifer to the upper aquifer, so it's very confounding. However, the one thing we knew for sure was when you got out at almost on the edge, and this happens to be Schoolhouse Road, on this side, we saw no exceedances in wells that were shallower. So by the time you move from the face of the landfill in the most general flow path, which is southeast, the landfill plume dives from the upper aquifer to the lower aquifer. So if you have a well and you are on this side of Schoolhouse Road, we can, with a great degree of confidence, say that that well is not impacted by the landfill leachate. So the people on that side of the street have an easier test to meet if they did want to keep their wells for irrigation. So if you happen to be on this side of Schoolhouse Road and your well was less than 100 feet in depth, and you could provide us, the Health Department Board of Health, with a test for 1,4-dioxane that shows that it is not exceeding the guideline, then you are allowed by variance, by Board of Health approval, to keep your well for that purpose. Much more complicated on this side of Schoolhouse Road. So what we are doing are taking each one of those requests separately. In no case are we allowed by the department to allow reuse of irrigation wells of those 39 properties that exceeded the guideline of 0.3. It is not up for consideration. Once it was identified as an exceedance, it's considered to be contaminated. So we are trying to take individual homeowner requests into consideration and give it a full and thorough one-by-one evaluation. So that is a difficult conversation because in some cases we're able to tell people yes, and some people we have to tell people no, you cannot keep your well for irrigation. And in some cases we're have to tell people you have to acquire more information before we can make the determination. So we have our regulations in place currently. We tried to make them as short as possible, but it is regulatory language, a little bit complex. I have them listed here. Basically tries to divide the area, as I just explained, that the area is not all one whole site. However, we are giving individual homeowners individual consideration. So I'm happy to say there is public health protection provided by the construction of Phase 1, which we was able to begin less than 4 years after the discovery of this contaminant in the environment, which is unbelievable, that we actually have water flowing to some of these homes as early as fall of 2016. We hope to complete the mandatory connection area by this spring. I am so proud to see this accomplished. I can't even tell you how much it means to me personally. 1,4-dioxane isn't just a problem here in Eastham. It's been found throughout Massachusetts. It's been found throughout the country. And as Laurel said, this isn't the only one. There are many more to follow. So we have to remain vigilant in wastewater protection, through our wastewater planning and through our water protection regulations and planning. You can see in Massachusetts alone that there have been so many towns that have had groundwater 1 exceedances. The difference here was that we had that problem with lack of a backup plan with municipal water available. And if we look across the country, now we're just talking about 1,4-dioxane, same story as what Laurel just described. There are regulations all over the place. Massachusetts, as you can see here, we are subject to a very, very conservative standard that provides maximum public health protection, but we were subject to a 0.3 micrograms per liter guideline. It's not a standard, a guideline. Whereas some states have no guideline at all. So it's an interesting time, I think, and it's an interesting conversation. Our investigation involved a lot of partners. We were very fortunate in that regard. We worked hand in hand with EPA, with DEP, and also with the academic community, Boston University and their Superfund research program, and people like Laurel that really came in and helped us to try to communicate this problem with the citizens. So I too am going to end with some lessons that I learned, and I think that we learned together as we went through this process. Number one, I was asked, like, well, why didn't we see this before? Why wasn't this detected? Well, you'll never see something you're not capable of finding. We actually have much more sophisticated laboratory analytical equipment that is able to detect those parts per trillion and very, very low limits. So that wasn't a way it was 10 years ago. So very low detection analytical methods have led to us being able to see these minute quantities of chemicals that we are consuming as in our drinking water. Number two, it's really difficult to see something if you're not looking for it. We weren't testing our drinking water wells for 1,4-dioxane because there is no drinking water standard. This investigation was driven by our responsibility under the solid waste regulation and guidelines that we're following pursuant to our landfill. And I think a really important part of this lesson is we need to continue to protect municipal water and our private wells forever. Our community will, throughout the areas that are not mandatory, we'll see wells continue, I'm sure, until we're probably not all here anymore. But so we're going to need to stay focused on protection. Lesson two, it really took a community to support change, and change is never easy. I don't like to change parking spaces. I go to the supermarket, I want to park in that same space that I park in every time. Change is not easy. We had to convince the community that this was a good move forward, and that this would add to their property values, and this was an investment that the community should be behind. Change is never easy. And those partnerships and collaborations. We couldn't have done it as a municipality. Staff couldn't do it. Consultants couldn't do it. It really took the citizens who spent endless hours supporting this issue, the consultants, DEP, EPA, and all those that I listed, and we really can't be thankful enough for their help in this regard. Lesson three, in terms of communication, I think we learned a lot. Number one, you can send people a lot of information, and if they don't understand it, you might as well not bother. You need to simplify the message and make it understandable. That was really a very important lesson we learned very early on. Education and outreach is very important. One method isn't good enough. In some cases, today social media is the big thing, but we live in a community where we have a lot of elderly citizens, and this was a very personal situation that occurred here, and we tried to inform people on a one-by-one basis if that was helpful to them, and group meetings, whatever works. So you have to use every method available out there for you. And in terms of risk communication, I think, again, it needs to be fair and balanced. At no time did we try to inflame or inflate the risk. We tried to keep this very focused and very balanced. And I think to keep credibility on your side, you need to maintain that level and that line of not overreacting, yet not underreacting. So in conclusion, 1,4-dioxane is considered to be a likely carcinogen, and it is on the EPA candidate list along with many others. Municipal water will eliminate the potential exposure and protect public health, but we need to remain vigilant in monitoring and testing our private wells in the future and also our municipal water supply. The best option, I'm a big person who's supporting prevention. Pollution prevention is the cheapest way around public health and environmental protection. So might that be something that we follow in Silent Spring's footsteps, that piece is really not to be understated. And this certainly wasn't an easy path that we had to follow, but nothing worthwhile ever seems like it ever is an easy path to follow. So maybe this is the answer. Reformulating, getting some of these byproducts out of our household products that we're using, like with phosphorus in years past. And with that, I will open it up to questions from anyone that might have one. Thank you. Sandy?
It's good that you decided to do questions at the end, because this is for both of you. In talking about not being overly reactionary or not being overly cautious, it was my understanding that the EPA was considering in its, not standards, but its recommendations, or whatever you're calling them, to lowering the 1,4-dioxane to 0.03 standard. They didn't do it, but at one point we were told that they were considering that. Do you know anything about that?
As far as I know, there is no EPA regulatory standard at all. So the only thing that currently exists are state guidelines. So there is no standard in place right now. It is one of many chemicals that's on a potential candidate list. Laura might have more up-to-date information about which ones are on the very top of that list, but as you know, EPA right now is sort of in a holding pattern, and I don't know if anything is in the works to follow in quick order, but right now we are following state guidelines, not standards.
And the 0.3 is that.
0.3 micrograms per liter for 1,4-dioxane.
In connection with Sandy's question, how, in a nutshell, if you can, does the state come up with the numbers that they're putting out? For example, why is there such a discrepancy between them? And why did, as far as I recall, and maybe I'm incorrect, we go from 3 to 0.3 during the process of choosing to bring to the public our desire to have public water?
We are following state guidelines, and at the Department of Environmental Protection, Massachusetts Department of Environmental Protection, they have a division called ORS, Office of Research Standards. And the drinking water guideline in their division was not consistent with the hazardous waste programs standard or guideline. In the course of our investigation, in the very early phase of our investigation, that inconsistency was brought to light. The fact that there was internal discord. So I believe it was late 2012 when our initial discovery occurred, November 2012, DEP's two separate departments got together and they agreed upon the lowering standard guideline. I'm sorry, I keep saying standard, just replace it with guideline, would apply across the board. So that is why in our very early investigation phases, we used analytical methods. We had endlessly lengthy discussions with the department about what analytical procedure we would use to be able to detect these very minute quantities of 1,4-dioxane, because it was not, again, how I highlighted, the analytical processes have to be there for you to be able to find it. So we had very few laboratories in Massachusetts that had the capacity to actually do the testing. So therefore, we reached an agreement with them that we would be looking at samples at the very, very lowest limits so that we would be able to comply with that low standard. That's a very long answer to a complicated question. But we were trying to be as responsive as we could as to the needs and be as conservative as we could. We definitely didn't want to have to go duplicate our efforts, test with an analytical method that didn't have the ability to test and detect at the lower limits. So that's why from the very beginning we wanted to be as conservative as possible.
Just to follow up on that, question. I mean, you kind of bring up a broader question. So with that graph that I had of PFOS and PFOA, the guidelines were kind of all over the map. And so what happens is you have people at EPA and you have people at DEP or other state agencies, toxicologists, risk assessors, and they're looking at the scientific information that's available. So a lot of what we know comes from animal studies. In some cases, we have epidemiological studies, so information from human populations who've been exposed. And so those people aren't necessarily doing the science or the experiments or, testing for the effects. They're sitting back and looking at all the available information. And so different scientists kind of come to different conclusions. Maybe they put more weight on human studies, or maybe with human studies there can be other factors that aren't well accounted for. So they kind of evaluate each study and decide how much weight to give it, how much they believe each individual study, and then they also apply certain safety factors. So for instance, if there's a health endpoint like if like infants or fetuses are thought to be more sensitive, then they apply extra safety factors just to make sure we're covering everyone. Sometimes they put safety factors in when the only information that's available is from animal studies and we're trying to extrapolate to people. So maybe we put a safety factor in there. Sometimes we use 3, sometimes we use 10. Why 10? 10 fingers. I mean, they try to be precautionary and put in extra safety factors, but there's different approaches, and like I said, just different evidence that gets weighted by different people. So that's how we end up with so many different guidelines. Like for instance, Vermont just came out with a guideline of 20 parts per trillion for PFOS and PFOA combined. New Jersey just came out with a draft guideline of 14 for PFOA alone. EPA came out with 70 last year for PFOS and PFOA combined. There's not much different science. They're just weighting it differently or putting different weight on different factors, and some people are more conservative or more precautionary, others aren't. So,
but I thank you for that, because when you see all those different numbers, I think the first reflex is nobody knows what they're doing, and so that was a really great answer. I think it's still unfortunate because it is hard to, when you're trying to convey risk, and you look at numbers like that, you say, well, I'm going to move to Vermont because it's safer. Well, not necessarily. So thank you for that.
Yeah. And one other factor to consider is often from the animal studies, we come up with, say, an amount, micrograms or milligrams of chemical per body weight. So if you're bigger, you can have more of it because it gets spread out throughout your body per day. So you get something like that. Like, this is how much it's okay to have. And we think that there's no adverse health effect linked with that. But for instance, 1,4-dioxane, maybe you can be exposed through other products in your home. These fluorinated chemicals we're exposed to in our food and many other ways. So there's also something called a relative source contribution. So how much are we kind of allocating that can come from your water? And so water suppliers are often like, we have to make our levels very low, but people are exposed through all these other ways. And so, again, risk assessors can come up with different conclusions about what that value should be. And there's some kind of default values, but people might choose a different value.
And the frustrating concern is that the future holds that there's going to be other agents that have been discovered, identified as potentially hazardous, and they'll also have a variety of numbers that are supposedly at risk or not at risk for, and so forth. So this will be a never-ending issue. I couldn't help thinking as both these presentations are excellent, by the way. I enjoyed them immensely. I couldn't help thinking that one of the solutions is going to be if someone comes up with the chemical ability to remove all of these, a lot of these agents from the water room.
Right.
We're very lucky here in Eastham because the up-gradient flow of water for our community water wells there's no manufacturing up there. There's no large, it's the Atlantic Ocean and a lot of the national seashores. So we're pretty safe for a long while to come. And the other thing I couldn't help thinking is the solution to most of these things that we're talking about today, there's a scientific element. There's also a huge political element. And when you try to put both those together, it's just so frustrating and so. well,
And
that-
then the economics
Well,
side
that-
too.
those
because,
two
yeah.
drive the economics.
But I think a way to get rid of it is great. And people, the one thing, and I think that is clear from your presentations are, people think, oh, well, you know, my water tested fine, or I have a filtration system. You don't know that a filtration system may or may not, in fact, most cases for some of for these things, it won't get out particulates. So I use my Brita filter. Pouring it through is not going to get rid of 1,4-dioxane that's in there. So that's a false sense people may have if they've just had their water tested for, say, a rental certificate. It's only these, 6 or 8 things. It's not going to be all these other things or 1,4-dioxane. Each of these tests requires a different type of test, different costs, and so.
And in response to that comment, there's not always correlation between, often there's not correlation, I guess I should say it in the negative, between routine parameters and what we see in terms of volatile organic compounds. So it is a false sense of security when you have only certain parameters tested that you've seen it and I've tested my water and it's fine. It's an unknown vast soup of what we're being exposed to. And I guess the clearest conclusion I can come to is you don't want to drink water down gradient of a landfill or wastewater discharge. So it's just an educational process that I think we continue to move forward, and we need to, as we both said, need to continue to stay focused on protection of the groundwater.
And I think water treatment will only get you so far. Like Jane mentioned, 1,4-dioxane is very hard to remove from using conventional technologies. For the fluorinated chemicals, it's this huge category with many chemical cousins that have different properties. So the long chain compounds, they're relatively easy to remove. So PFOS and PFOA, you can put in basically a gigantic Brita filter, and the activated carbon will remove those. So you feel like, okay, great, dealt with the fluorinated chemicals. But the new ones that they've put in, the shorter chain compounds, they don't persist as long in our body, but they do move through the environment more quickly. They're kind of more mobile, less likely to stick to the soil, less likely to stick to activated carbon, more likely to get accumulated by plants. So I worry a little bit that we think we've dealt with the fluorinated chemicals by putting in activated carbon and we're done. And if we're still using them, we're going to have other fluorinated chemicals, and so the treatment might not work for that. So, you know, sort of moving further upstream and saying, like, the idea of putting highly persistent chemicals out into the environment, like maybe we need to do it for firefighting foams, we don't have a good alternative yet, and that's like an important use, and obviously we want to be able to put out fires when they happen. But do you need that on your couch? Do you need that in your burger wrapper? You know, where can we now look to avoid using them and then find alternatives that are less persistent and less harmful? It's a combination. Mm-hmm.
Okay. Anyone else? Thank you so much for coming.
Thank you.
Thanks, Laurel.
Thank you both.